The previous lecture, if you remember, we have studied about some stress and strain, and then the modulus, young modulus, bulk modulus. That's what we have studied in the previous lecture. The last topic that we have studied in the previous session was bulk modulus. There was a bit of holidays in between. I think it was due to the unit test actually that you were given. So I hope that unit tests that you have taken were good. Tell me, how was your unit tests? And so after that, we are going to start the session. I hope the previous topics were clear in your mind. Have a look at that. What we have studied, that ratio of stress over strain is a constant. That's where we were discussing things. Ratio of stress and strain is a constant, and that constant is named according to the nature of stress or type of stress or strain. So in this series, we have studied young modulus. That was the ratio of longitudinal stress and strain. Next, we have studied bulk modulus. I will show you what we have studied in the previous session. That was the bulk modulus. What was that? Volumetric stress to the volumetric strain. Now, in today's session, this is a simple definition. This is a definition kind of thing. What is compressibility? Compressibility is nothing but the reciprocal of bulk modulus. This is a simple definition. Sometimes it may come in form of definition or in a simple numerical type of thing. What is compressibility? Compressibility is the reciprocal of bulk modulus. Bulk modulus we have studied in the previous slide. Reciprocal of that quantity is known as compressibility, or you can say it is denoted by K. It is denoted by K is what? 1 over B. B is what? Bulk modulus. So this is compressibility. Okay, I hope this is clear. Nothing special in that. Just keep it in mind. Now, today we are going to start a new topic. Again, there is one more modulus actually left. This is shear modulus. The another name of this shear modulus is modulus of rigidity. Rigidity is the term that you know well. Rigid bodies. It is the term related to the rigid bodies. So modulus of rigidity. What is this? Definition is on your screen. The ratio of shear stress. Shear stress, another name of shear stress was that was tangential stress. That was tangential stress. So you can say, do you remember tangential stress? Whenever the force acts on a body parallel to the surface, then the stress produced is known as shearing stress or tangential stress. For example, have a look at that. This is a body. This body, if you see with the dotted lines, this is the actual body, front view of the body with the dotted line shown. This is the actual body. Now what I'm saying that a force F is acted on this surface, on the top surface in the right side. A force F is acting like that. So this force F is tangential to the top layer, and this top layer displaces by a distance x. This distance displaced is x, and the angle displaced is theta. So what is shear modulus? Shear modulus is denoted by eta, and what it will be? Shearing stress over shearing strain. I think things are clear that ratio of stress over strain is known as modulus. What modulus it is, it depends on the nature of the stress. Now, shearing stress is what? If I say shearing stress is what? Force per unit area. But you need to remember force is to be taken parallel to the surface. For example, if a body is like this, I'm just giving you an example. If a body is like this and force is like this, F, at an angle theta, then in this equation, force will be what? Force will be taken parallel to the surface and that force will be F cos theta. So what you will take F cos theta. So I am writing it here F parallel. F parallel divided by A, this is stress, divided by strain. Strain is what? I have told you that shearing strain is what? This angle theta. So tan theta is what? If you calculate tan theta will be x by L. X by L. So this shearing modulus will be F parallel into L divided by A into. Try to figure out each and every term in it. What is A? Area of the surface. X is what? Displacement of the surface. F parallel, force parallel to the surface. L is what? L is the separation between the two surfaces, the fixed surface and the displaced layer or the displaced surface. The separation between these two layers is known as L. So remember the formula, remember the stress. You can easily calculate these modulus in the numerical actually. There is no worry, no strain, take no strain to remember this formula actually. But keep these things in mind. After that, I can move further. There is one more thing. This is Poisson's ratio. What is Poisson's ratio? Don't go with the definition actually. We will go with the definition later on. First of all, let's think about one thing. Suppose you have a wire. Wire is of cylindrical shape and you have a wire. Now listen to me very carefully. You are applying some force. You are applying some force like I will show you. For example, you are applying a force F on it like this and a force F on this side as well. What will happen? Just tell me what will happen. This wire will get stretched. This wire will get stretched. And can you notice that if this is a wire, then the volume of the wire will remain same. If length is increasing, then the diameter of the wire should decrease actually. You can see it here like this. Can you see that wire? If you stretch the wire, it will look like that. Initially, it was this one, and finally, it becomes longer, but it becomes thinner. So, what I'm saying, let's suppose few things here. Let's suppose its original length was L, and new length becomes L plus delta L. That means length is increased by an amount delta L. And in the lateral direction, I will say let its original width in this lateral direction is D. And after stretching, it becomes or it decreases by delta D. So it will become D minus delta D. Are you getting my point? Original length was L. After stretching, it becomes L plus delta L. While the length increases, its width decreases. So the change in the width is D minus delta D, or you can say delta D is the change in the width. So what is Poisson's ratio? It is denoted by sigma. It is denoted by sigma. So what is sigma? Sigma is, now you can study from the definition, ratio of lateral strain to the longitudinal strain. What is lateral? What is longitudinal? You have learned well. Longitudinal is what? Change in the length divided by original length. And lateral means the direction which is perpendicular to the applied force. Lateral means what? The direction which is perpendicular to the applied force. Force was applied perpendicularly in the x direction, or you can say force is applied in the x direction. And we are talking about lateral, then that means in the y direction. So you can, from the diagram, lateral strain is what? Change in lateral direction is what? Delta D. And this width is decreasing, so you will write minus delta D divided by original width was D divided by longitudinal strain. Longitudinal strain was change in length. Change in length was delta L. Original length was L. So you can say sigma is what? Negative of delta D into L divided by D into delta L. I have done nothing in this, just going with the definition and creating a formula for you. You can either remember the definition or remember the formula. That's up to you. The thing is that if you stretch a wire, its diameter will decrease. If you stretch a wire, its length will increase and diameter will decrease. And the term relating these two strains is known as Poisson's ratio. Poisson's is what? Poisson's is the name of a scientist, nothing else. Don't take it otherwise. It's a name of a scientist actually. So you can check the spelling as well. Uh, this is the name of the scientist. Okay. So these are the basic things, the definition part. Now we are moving towards a more critical thing, a more mechanics thing actually. So I hope you will be understanding the things well now. Have a look at the definition. Have a look at the heading first. The heading says the work done in stretching a wire, or you are saying the potential energy of a stretched wire. This is the main topic. Most of the questions usually come from this one. So now what I'm saying, first of all, let's have a look. Consider you have a wire. You have a wire, cylindrical wire, and this wire has a length L. This wire has a length L. Clear? And area is A. Area of cross section is A. And this wire is suspended from a ceiling. This white line is a ceiling, is suspended from a ceiling. I think till this point, everything is clear. Now you have applied a force at this end. You have started stretching it in the downward direction. And let's suppose the total elongation that you have given to the wire is L. So you have stretched this wire by a distance L. Like this. This is the original length. And from original length to this length, you have stretched this wire by a distance small l. Clear? What you need to do, you need to calculate the potential energy stored in the wire. I think thing is clear. Now listen to me very carefully. Why the potential energy will get stored? If you stretch the wire, it will try to oppose. It will try to oppose due to its elastic nature. And if it is trying to oppose, then you need to work on it. You need to work on stretching the wire, and this work will be stored in the form of potential energy. Whenever, remember, just remember from the previous classes of previous chapters of work, energy, and power, whenever work is done against the conservative forces, then this work done gets stored in the form of potential energy. If you are doing work without any acceleration. So what will happen if you stretch the wire? You are working against the elastic energy, against the elastic forces. So that is a conservative force. The work you have done will be stored in the form of potential energy, given that you are stretching it slowly, slowly, slowly. Clear? So in this situation, what you need to do, you need to calculate the work done. So let's consider a intermediate situation. This is the initial situation. This is the final situation. I for initial, F for final. Let's consider an intermediate situation like this. What I am saying that in this situation, wire is stretched by a distance x only. Wire is stretched by a distance x only. Clear? So now, what I am saying, in this position, what will be the value of force acting on it? Force F acting in the position when elongation was x. When elongation was x, then what will be the value of force? What you know that Young modulus is what? We are talking about longitudinal stress and strain because you are pulling a wire, you are stretching a wire. So this will be the case of Young modulus. So what is the Young modulus? We have studied in the previous session that y is equals to F L over A delta L. That's what you have studied, I think. If you remember, Young modulus is what? Stress over strain. Stress is what? Force per unit area. Strain is what? Delta L over L. So if I place the values according to our situation, then it will be force, let's suppose is F, area is A, L is the length, original length, that is L, divided by delta L is what is the change in the length. So in this second stage, change in the length is X. So if you calculate the value of force, what the value of force F is equals to Y, you will transfer A into X here, A X divided by L. This is the value of force. Why we are calculating the force? Because we need to calculate the work done. What we are going to do, we are going to calculate the work done, and this work done will be stored in the form of potential energy. So we will get the answer for potential energy. So what I am saying, let's change the color of the pen. Work done. Now we are in the position of X. Now displace the wire again by a very small distance of delta X. I am again displacing it by a very small distance delta X. From where to where? From X to delta X. So work done in stretching the wire from X to X plus delta X. This is a common practice. Whenever you need some work done in variable situations, then you need to do this thing. So what is the work done? You will say small work done dW is equals to force into displacement. Or you can say you can choose a very small displacement of dx. Force is what? Y A X divided by L. This is force. What is the displacement? Dx. This is the work done in a small displacement dx. Now the total work done will be, I will say, total work done. You will say work done is equals to Just integrate this term, integration y a x by L dx. This is going to be the total work done. Now I am calculating the total work done here. Work done is equals to, take the constants out of the integration. Y a by L is a constant. What will be left behind? X dx. What will be the limit of integration? You are stretching the wire from its natural length by a distance L. So if you say limit will be 0 to L, 0 to L. Now integrate it. You know the integration. Y a by L is there. Integration of x is x square by 2. Limit will be 0 to L. You can solve it. You can write it in another way. What will you write? After putting the limits y a by 2L, it will be L square minus 0. So it will be L square. This work done is stored in the form of potential energy. So the potential energy will be y a L square by 2L. Just have a look at the relation y a L square by 2L. Now remember two or three things here. What is y? Young modulus. A is the area of cross section. L is what? Extension or elongation in the wire. Capital L is what? Original length of the wire. I think all these terms are clear. Small l is the elongation in the wire. Capital L is the natural length or original length of the wire. I think it is clear. What we have done here, what we have done, we have considered an intermediate position of extension of elongation x and then calculated the work done for a small displacement dx. After that, for complete work done, we have integrated it, and after integration, we got the answer. If you have any doubt, you can ask me. Otherwise, I am moving further. If the screen is visible, completely clearly visible, say yes. Otherwise, you can say that it's not that much visible. You can ask, you can say anything. But today, I'm seeing some new faces actually. I think JNB Vishakhapatnam. I think this is a new school actually. I think you were not present in the previous classes, I hope. If correct me if I am wrong. So now moving further, you need to remember this relation y u is equals to y a L square by 2L. Y a L square by 2L. Now again, moving on the next slide. Key formulas. What we have studied till now, that potential energy stored U is y a L square by 2L. This is what potential energy is stored in the wire. Sometimes it is not advisable to use this formula, or you can use different form of this formula. So I am writing some different forms. For that, you need to remember some basic things actually. You need to remember some basic things. Or I will say you need to recall the previous things. Like what are the previous things? First of all, what is Young modulus? Young modulus is what? Stress over strain. Clear? I think it is clear now. One more thing. Y is what? If you place the value of stress, that is this one, force per unit area. And if you place the value of strain, that will be delta L by L. or you can say L by capital L. This is the formula for Young modulus. Now, I will use these relations later on in the formation of new kind of formulas. First of all, just multiply the equation by L and divide it by L. Just do it for once. Multiply and divide with L. Now, potential energy will become, if you say this A and this L, A into L is what? A is the area of cross section, L is the length of the wire. Can you say that A into L will become volume of the wire? So I will write A into L as the volume. Volume. This volume came from A into L. Clear? There is a 2 in the denominator, so I will write 1 by 2. Clear? Now, have a look at that. This small l upon capital L. This small l upon capital L is what? L is the change in the length. Capital L is the original length. So change in length upon original length is what? Strain. So it will be strain. I hope you can listen those things. I am using the term strain for what? 1 L and 1 capital L. Change in length over original length is what? Strain. Now what's remaining? What's remaining is Y is remaining, 1 small L is remaining, and 1 capital L is remaining. Clear? If you see here from this formula, Y small l over capital L. Y small l over capital L is what? F upon A. And F upon A is nothing but stress. So for the remaining part, I can write stress. So it will be, sorry, U is what? Half into stress into strain into volume. This is the most golden form for the potential energy. Most fundamental and most basic form. If you remember, this relation can be remembered quite easily as compared to the previous one. If you have any problem, you can tell me. What I have done, I have multiplied with L and L, capital N L, capital L. After that, I have transformed the formula. You need to remember this formula actually. What is the potential energy of a stress wire? You will say half stress strain into volume. Clear? Volume is what? Volume is what? Area into length. Strain is what? Change in length divided by original length. And stress is what? So all these terms are mentioned here. If you need to write it down, you can write it down. Now I am going to convert it in another form. I am going to convert it in another form. Have a look at that. U is what? Half. From this equation, have a look at that. Can you write stress as Y into strain? From this relation, can you write stress as Y into strain? Yes, sir, you can write. So I am writing stress as Y into strain. This is what? Stress. There is another strain. So it will become strain square into volume. This is another form that we quite most of the times that is used. I think this is another, again, a clear term. Now in the third part, what we can do? We can change the strain in terms of stress. If you change the strain in terms of stress, then what we will get? Strain is equals to stress over Y. Strain is equals to stress over Y. So again, you can write U is equals to 1 by 2. Stress is already there. So it will become stress square divided by Y into volume. So these are the three relations. You can pick either, actually, you need to learn all of them if you want to save time. Otherwise, you can remember at least one of them. And at least one of them should be this one. If you know this relation, you can transform it into anyone. So I request you to remember this relation. I think all these relations are clear in your mind. We are going to use these relation in the numericals in the concept test that we are going to discuss further. So just make sure that you have taken the screenshot or you have mentioned, you have written everything on your notebook. Otherwise, you will not be able to solve the attempt the question. I hope it's clear. So moving further on the next slide, let's see what's on the next slide. If you have any doubt, you can ask. What is energy density? This is again a simple term. You will learn these things quite many times. Energy density is what? Energy stored in the wire per unit volume. This is the total energy stored in the wire. This is the total energy stored in the wire. Then what is the energy stored in the unit volume? That is called energy density. So energy density is what? Energy per unit volume. Energy per unit volume. This is again a simple term. I will mention energy density is what? Energy per unit volume. If I say, then what are the formulas for energy density? You will say divide the energy by the volume. And if I look at the previous slide, in all these formulas, there is a term volume. If I divide this energy with the volume, this volume term will be cancelled out. This volume term will be cancelled out. So what you will get, if you remove the term volume from here, you will get energy density. So what will be it? Half stress into strain. This is what? Energy density. Energy density, U for energy, D for density. There might be some other symbols as well. One term is this. Again, you can write it as in the this separation. In this, you can remove the volume. So it will become half Y into strain square. That will be half Y into strain square. What is Y here? What is Y here? Can anyone answer? What is Y? This simple term you can answer actually. I think this is clear. I don't need to explain it further. Okay. So I'm moving further. You can write one more formula for that. Energy density is equals to 1 upon 2 by stress square. So all these terms are related to energy density. 1, 2, and 3. I hope it's clear. Now, you didn't answer actually. What is Y? Y is the young modulus, na? You know the term, I think. Moving further, let's take a concept test. I hope you have taken the screenshots. Now take a concept test. The first question on your screen, you have time of 1 minute. You have the time of 1 minute. Just solve it out. And I'm actually giving you 1 minute for this. First of all, identify the data. First of all, identify the data. I will not speak in those remaining 30 seconds. Anyone got the answer? Just raise your hand. How many of you have identified the data, that what is A, what is small l, what is capital L, what is Y? How many of you have identified the data actually? So first of all, I am mentioning the data here. A steel wire of 4 meter in length. So this is the original length. Steel wire of 4 meter in length. That means capital L is given as 4 meter. Very good. Next thing is stretched through 2 mm. It is stretched by a distance of 2 mm. So stretched by 2 mm, that means small l. Small l is given as 2 mm. 2 mm is what? 2 into 10 raised to the power minus 3 meter. Is it clear? The cross-sectional area of the wire is 2 mm square. Again, 2 mm square. So cross-sectional area is denoted by capital A, is 2 mm square. Mm square is what? Again, mm is means 10 to power minus 3, square means 10 to power minus 6. So it will be 2 into 10 raised to the power minus 6 meter square. Till now, everything is clear. And now again, one more thing. Young modulus of steel is what? Y is equals to 2 into 10 raised to the power 11 Newton per meter square. So this is what the data is. Now we need to calculate the elastic potential energy and the energy density. So I am calculating the potential energy stored in the wire. U. Change the color of the pen. This one. So U. U is the what? Energy stored in the wire. You can use either of the relation. So here everything is mentioned. I am using the basic formula, and that basic formula is U is equals to Y A L square by 2L. Y A L square by 2L. I hope this one is correct and you remember the formula. Now just place the values. After placing the values, you will get Y is what? 2 into 10 raised to the power 11. A is what? Find out. A is what? 2 into 10 raised to the power minus 6. Small l is what? 2 into 10 raised to power minus 3. If you square it out, it will become 4 into 10 raised to power minus 6 divided by 2 into L. L is what? 4. Now you need to cancel things out. 2 will be cancelled by this 2. 4 will be cancelled by this 4. I think it's clear. So U will be, this is 2 into 10 raised to power minus 6 minus 12 and 11 minus 1. That is 0.2 joule. I think this is just formula based question. Next part is calculate energy density. Energy density is what? Energy per unit volume. Energy per unit volume. That's what the thing is. So energy per unit volume. What is the volume? Volume is what? A into L. A into L. So you can place the values. Okay. Energy per unit volume. So energy is what? 0.2. Volume is what? A into L. This is what the volume is. Now again place the values. UD is equals to 0.2 divided by area is given something 2 into 10 raised to the power minus 6 into length is what? 4 meter. Clear? I think it will be 2 and 2 will cancel out. It will remain 0.1. So it will be 1 by 4 into 10 raised to the power. This is minus 6. It will go up in the numerator. It will become positive 6. And there is a 0.1 that is minus 1. So it will become 5. I hope I have mentioned it correct. So energy density is 0.25 into 10 raised to the power 5 joule per meter cube. Let's check the calculation. Otherwise, the concept is, I hope, clear in your mind. If you have any doubt, you can ask. Otherwise, I am moving for the second question. Just be quick actually in that as well. This is a formula based question, so no worries about that. I hope you know the answer. This is a previous year question of 2020. Have a look at that and try to solve it out. JNV Akola, you can solve the question. Answer it in the chat box very quickly. Again, you have 1 minute of time, na? 1 minute of time. Should I start? Wait for 10 more seconds. Okay. Have a look at the answer. Answer is B. B is what? Root 2 is to 1. So now solve it out. There are various formulas for the energy stored in the wire. You can use either of them, but you need to pick in a smart way. Which formula is going to be used? You need to pick that in a smart way. So what I'm saying, if I say that energy stored, you know that energy stored in the wire is 1 upon 2y into stress square. If you don't remember the relations, it will be difficult for you. Why I am using this? Because they are asking the relation in terms of diameter. They are asking the relation in terms of diameter. So I need to bring that term. Na? And length, original and change in length is not mentioned. Are you getting my point? What I'm saying, the formula was half stress into strain per unit volume tha, so volume will be missing here. So half stress into strain. So if you want to calculate strain, you need to know the original length and the change in the length. But that thing is missing in the question. So I need to eliminate this strain term. For that, I have used the formula 1 upon 2y stress square. I hope this is clear why we are using this relation. Now again, this is energy density. Again, in the next step, I will write 1 upon 2y. Stress is what? Stress is what? Force per unit area, and this is squared. Just listen to me very carefully. What is this force? Force applied on the wire. And the question says suspended from a ceiling under the same load. That means wire is suspended with the same force. Then if same force is acting on both the wires, that means force will be same. Again, if I say 1 upon 2y force and area is what? Pi r square. You know the area pi r square, and that is of whole square. I think there is nothing to worry about those terms. Why we have transformed area into pi r square? Because we need to find the relation with the diameters. So if you calculated the relation between radius, the ratio of radius, then it will be same as the diameter. So there is no problem with that. I think now just find out the constant terms in the question. According to the question, wires of same two steel wires. Wires are of same material. That means Y is constant. Load is same. That means F is constant. 2, you know, is a constant. Pi is a constant. So you can see that energy density, if I remove the constant, is proportional to, or you can say inversely proportional to 1 over, this is R square over whole square. That means R raised to the power 4. I think it is clear. The term I am mentioning, everything is constant, so we can use a proportionality sign. So now what I can write, energy density for first wire divided by energy density for second wire is equals to, this is reciprocal now. So it will be R2 by R1 whole raised to the power 4. And the ratio of energy density is given as 1 is to 4. So it is 1 is to 4 is equals to R2 by R1 whole power 4. Again, if you need to write this, R2 by R1 will become fourth root of 1 is to 4. So R2 by R1 will be 1 is to root 2. So R1 by R2 will be root 2 is to 1. This is what our answer. I hope the question is clear to you. Just don't try to remember the question. Don't try to understand a particular question. Try to understand the concept actually. This is a basic concept that I have done. I have derived a relation between the quantities. This is the relation. This is the ratio of radius. And it will be same for the diameter. Na? You know the diameter is twice of radius. So relation will remain same. Ratio will remain same. So what I'm saying, I have achieved a relation between the required quantities, removed the constant, and then created a ratio. This is what happens. I hope it's quite, actually time is up. So I hope you understand the concept well. So I am ending the class here. From the next class, after discussing a few topic like this one, stress strain curve, we will move further towards the next chapter that is going to be about fluid. And you have not replied about your UTs. Just send me the reply whether you have done it or wrong? What was the how was your UTs? So till now, I think chapter is just towards the end. We will discuss some PYQs again in the next session. After that, it will be end of this chapter. Till then.